the engineering frat, Theta Tau reached out and they want to have a volleyball tournament fall term. So they'll be sending out a when to meet about that. So that's something to look out for. Also, this person from Gather, I've never heard of it before, reached out to me about sponsoring an event, and I originally didn't respond because I didn't know whether it was legit. I should have done at least a Google search on it, because it looks like it's actually, they could have actually helped us, but I responded too late for us to for them to actually sponsor us. I don't know, they didn't have much information. I was worried it was spam, actually. It's just like a social media app for planning. Regardless, they said I could reserve a spot for us. I might set that up, I might not. It's just a matter of me having enough time to do that. Can I just do like a follow-up today? Okay, cool. Anyway, welcome Alicia. She's connecting. Welcome Alicia. Welcome.
Okay.
Right, we have to talk about a few things in regard to the project, mostly the scoring function. So in the last week, I connected some things. So let's just go through to make sure everyone's on the same page about how to run this. So I'm in the time series forecasting directory here. This is what you'd pull from Git. And we're going to run Python 3 or Python and algorithm. Sorry, before I do that, we have to load in the virtual environment. So I don't think that I actually push the virtual environment, do I? Yeah. So what you have to do is you have to run Python 3 -m venv. That creates a virtual environment for this. So I will just remove the virtual environment we have. Actually, I won't do that. You run the command to create the virtual environment, and then you have to do like pip install -r requirements, and then that'll install everything. And once you do that, you can just do source venv bin activate, and now we can use all the modules in the virtual environment. And to run algorithm.py, you just do that. And we don't have a main method set up. At least I don't have the main method set up to do anything important. So what I've been doing is I've just been copy and pasting for development. Sorry, we have to do Python 3 -i to make it interactive. I have an alias in my bash RC PI that's saved to here, I'll show you this. It's pretty useful. People don't often do this. I set up aliases on my computer. So for instance, if I want to go to my desktop, I do cdd. That's because I set up an alias in my bash RC. So if you go to like bash RC, you can see all the aliases I have. I think if I even do aliases, it'll list all of them. They're just common commands I use. So if I want to go to like a projects folder on my desktop, I do cdp. If I want to run Python, I just do PI, and it runs with Python in interactive mode. I think it's pretty useful, and for SSHing, it's really useful actually. That's just a note. So yeah, so if you haven't downloaded if you haven't downloaded the data yet, you want to do that. Otherwise, you're going to give it a you're going to run the load data command without the tempter function, without the tempter parameter, and it'll load in the data. Right now, we're just doing 50 patients. I talked about last time how, yeah, if you haven't downloaded the data, you're going to not set this, and then you wouldn't give it a tempter. It'll return a temporary file, and then you're going to move that data to somewhere on your hard drive that is persistent. or more persistent than the temporary directory, because the paradigm of load data is it just downloads the data into your temporary directory using the tempter module, which is somewhere up here. Yeah, it uses the temp directory module from temp file package. Okay, so now we have data that looks like this. It is 50 patient files, each with 100,000 points. And then we can use get segments to get the X and Y. So for each patient file, we're grabbing one sample. So right now, the default is set to so that each patient file has 64,000 points for the features, and then the Y has 128 points or 128 features for each patient file or for each sample. And X and Y are built in such that these are adjacent to one another. And then right now we're not going to run the genetic algorithm. I'm going to go to where this is called. And what we can do is we can run this run this to get the sparse model. And what this will do is it'll build the sparse dictionary in addition to the sparse model of X, of all of X. And I think that's okay. I think we can do that because we're using only the data that are the features, and we want to evaluate how well we can predict the predictive variables, which are the Y's, which are the 128 points after the 64,000 points. I don't know if this is an okay distribution. I do know that the shape, the number of points has to be a common multiple of 32, because that's the batch size we use in the sparse model. The reason I'm bringing this up is because when we do prediction, and I'll show you what happens and we do a couple sample runs, we're going to get two variables, and I haven't decided on, we're going to get two matrices, and we have to score those matrices according to how well they align with each other. We're going to get the activity matrix of the predicted variables with the dictionary from the sparse representation, which will be right here. And we have to score that, and I'm not sure how to do that yet. This will likely take a long time, so I just want to, I'll stop for questions. Does anybody have any questions for the workflow of the pipeline that we have going on right now, or how you'd set this up? I would like it so that all of you could reproduce this. I've tried to make it as reproducible as possible.
I have a question. So,
Okay.
so when do you think we're gonna get everything done by for the algorithm and the module and stuff?
The last thing is a scoring function, and then we run experiments.
Okay, so then after we finish that, could you maybe like go through all of the functions and like say like what they do specifically and how it all pieces together? That's like after we finish everything now.
Yeah. Do you have any, while we're waiting right now, do you have any questions on any of them specifically?
No, not really.
Like, do you have any questions about it conceptually either? I think that understanding conceptually what's going on is more important than understanding how it's done specifically. There's often details can be fleshed out in different ways.
Not at the moment.
Okay. But what's in this main method is the workflow, right? You're loading in data for each patient file, you're acquiring features for each patient files, and then you're running the genetic algorithm. In the genetic algorithm, you're applying the sparse representation onto all of the features. And then what we're doing is we're doing a k-fold cross-validation. Actually, we're not doing a k-fold cross-validation. We're I know it says k-fold, but it's really just to split up the training and testing set into um, the the n generation. So if we're doing if we're doing 10 generations, we just want to split up the data equally into that. And that's exactly what, you know, if we look back to the way we wrote out the algorithm systematically, if PowerPoint would open, I'm going to go back to a drawing right here. Right here. I keep going back to this slide, but it's important to understand what's going on. All right, so in this case, we're using the k-fold for n generations because we're looking at L generations, so like L and n generations, the same thing, and then we're looking at k children, where k is also n children, and then we're for each generation we're looping through that many children, and we're predicting the weights, uh, we're predicting the data and returning the weights, and then we are scoring how well the y prediction can be reconstructed by the sparse representation of the input data, which is of x, which we get in the beginning. And then after that, we are I haven't tested this part. I kind of just wrote that roughly. I've tested everything up to here, and what we really need to flesh out is the score function, which is scoring how well the reconstructed the reconstruction of the predicted values from the from the forecast, the time series forecast, how well or whether we optimize that activity. So like you could kind of think about, I hope I'm getting better at explaining this, but you can kind of think about, if we go onto the whiteboard, you can kind of think about like sparse coding, as in we have like these dictionary elements, right? In images, they're like patches. In our case, they are not patches. They are like, what's a better way to do it? In images, they're patches like this that could be used to reconstruct an image. We call that R. In our case, we're not dealing with patches. We're dealing with, so if this is time, and this is like X, this is like time series. In our case, if we have a blue dictionary, our patches would just be like areas of this that are composed of just these features. So you can imagine that if we have so many dictionary elements like this, so in maybe in a basic term, we just have like a sliding window, which represents like everything inside of these blue squares are dictionary elements. So this little curve forms a dictionary element. This upside down curve is a dictionary element. This rise to a peak is a dictionary element. You can imagine that when you want to reconstruct an image, there are certain contributions of these dictionary elements to the reconstructed image. So let's say, or reconstructed signal. So let's say that we have a new signal, which we will have in purple right here, T X prime. And if we're trying to reconstruct X prime using that, there's going to be an associated, so like, let's say maybe we take contributions of the dictionary element. So we take like this part of this first dictionary element here, and then maybe we take like this part of this dictionary element, but we also, and that you can use linear combinations of the dictionary elements. So, and what happens in the sparse model is that usually the contributions of these dictionary elements are sparse, such that you use 100% of one dictionary element at a time. So it's less likely that you'll use like 90% of dictionary element n and 10% of dictionary element n minus 1. Instead, you'll use just one dictionary element at a time. That's the sparse and sparse coding. But these percentages you can think of like activity. So there's an associated activity with a reconstruction, and we're trying to maximize that activity. That's the idea. We're trying to maximize that activity, because when that activity is maximized by some metric, that means that we are able to reconstruct. That means that our predictions are matching that of the training set, and that's how we know whether our time series forecast it makes sense. So what we're going to get, and I can show you. Oh, I lost my whiteboard. What we're going to get, and what I think we're going to get. I'm sorry. Okay. What we're going to get, and what I think we're going to get, is we're going to have two matrices. One matrix is going to be, actually, we might just get one matrix, which is a sparse activity. And that would correspond to the contributions of each of these dictionary elements in the reconstructed signal. So that would be like that'd be R of X prime. And that's what we're effectively trying to do here. Really, I should have drawn X prime and then the reconstructed version of X prime, which would be like R of X prime. R means reconstruction. So we're going to get the activity of the dictionary when you're creating R of X prime from X prime. Yeah. And then we have to score that activity we have to score the activity given the sparse model. So the score, I'm using a mouse pad. I'm going to score what's the score of, let's say, X prime. Actually, let's use, it's really Y prime. Actually, Y given the sparse model, or given the dictionary that we have. We have to create that, and that's what the function score is currently trying to do. Yeah. So on a very high level, we're using a dictionary and we're using the dictionary of a sparse model to find the reconstruction of Y. So RY, and then with that reconstruction, there's an associated activity of the dictionary of this dictionary with respect to R of Y, and we gotta score that somehow. Yeah, it's a very convoluted way of explaining that, but I want to make sure I just want people to understand it conceptually, so I'm trying to explain it in a variety of ways. So like Andy, on your point, that's what this score function does. It takes in the predictions from from a given child of a given generation of the time series forecast, which is an LSTM model, and it takes the sparse activity. The sparse activity is from sorry. Really only to take in a sparse model. Give me a second, I have to change some things. What I have to change is I have to change such that the score is only looking at the sparse model and the prediction. So we're going to look at the sparse dictionary. We can get the sparse dictionary from the weights of the sparse model we pass in. And that's before we call it. And then after we call it, we're getting the sparse activity. I don't even know if we need the sparse dictionary, if we need to record that, because that's saved in the sparse model. Yeah, we don't. But we need the activity after we call the sparse model. So sparse model.call, I had to ask Osamu about this because I wasn't sure what that does. If you look into model.py, activity, sparse model, call. I think this does dictionary learning, but it doesn't alter the it does reconstruction, but it doesn't alter the dictionary of the sparse model, which is important for us. So the score function is only going to take the y-pred, which is the predicted values from the time series forecast, and the sparse model, which is the reconstruction of the input signal. Yeah, okay. And then we don't need sparse dictionary here. We only need a sparse model because that's what we pass in right to the score function. Yeah. Whew. Okay, cool. And then we form a reconstruction. And once we form a reconstruction, we simply need the activity of the sparse model after that reconstruction. So this activity corresponds to this y-pred reconstruct, and we need to score this sparse activity. And I'm not sure how to do that because there's a there is on the sparse model learns, or the sparse model reconstructs an image or an input signal with a sparsity coefficient. So, right, if you think about with a sparsity parameter, so if you can kind of think of it like we have a matrix. We have a matrix. Sorry, drawing on Zoom was easier. We got a matrix where each element it corresponds to a dictionary element. Or maybe, sorry, let's say each column corresponds to a dictionary element, and then this is its relative contribution in the sample. You might have like 100, or sorry, we can just use one. You might have one here, one here, one here, one here, and then the rest are zeros. And that's the sparsity, as opposed to having like 0.1 here, 0.4 here, 0.3 here, something like that. But I want to look at the data before I think that's a general gist. I know it's represented as a matrix, but I'm not sure if it's per sample on the columns or per sample on the rows. I'm not sure. Cool.
So Ethan, does it have like 100 children per column? Is that how the children are fit into the generation?
Okay, yeah. So for each child in each given generation, we're going to have a different sparsity matrix. That sparsity matrix, the way I think it's interpreted is that's the contribution per each dictionary element, per each sample. That I think so. I think the activity matrix is like dictionary element sample, dictionary element by sample. I think that's the dimensions of it. Yeah, I should have ran this ahead of time, but I fell asleep. There's a stopping parameter on this, so this shouldn't proceed. There's an early stopping parameter, I'm pretty sure, so this shouldn't proceed too far. But I do appreciate the questions because it helps me explain the general scheme, because I want to make sure that when we're all collaborating on this paper, I want to make sure that we all understand what's going on. We still have the sparse, there's sparse coding with Savek fleshed out as background. I think the genetic algorithm is more of now we have more of a background on it, and I think we still need more of a
Yeah.
background on the time series
Yeah, I'm yet
forecast.
to add stuff. I'm yet to add stuff in the genetic algorithm stuff.
Okay.
But
And then
mistakes always.
in the methods, this is where we really take into account the algorithm we're implementing, in addition to the network architecture of the LSTM. We might have to add some stuff in terms of, okay, it finished. We might have to add some stuff in terms of the network architecture of the sparse model itself too. I have to talk to Osama about that. So now that we finished this, we have the sparse model, right? I know I returned sparse dictionary, but we only really need the sparse model, okay? Weights are set to none. We are concerned with 100 children per generation, and we're going to run the forecast for at most 200 epochs, and then our alpha is 0.05, and that means that we are concerned with only the top 5 children per generation. We're going to do a k-fold. In generations we have 10 generations. Okay, we are going to do k-fold validation to control the splitting, and what I'm going to do is I'm just going to do something easy. There we go. So now we're just grabbing the last one. On this. Okay. So for the first child, we're setting the weights to random, and then we're using the predict forecast to return ypred and weights. When we look at predict forecast, what it's doing is it's first scaling the inputs, building the model. If weights is set, it's setting that to the first layer, and then it's doing a fit. It's predicting. It's grabbing the weights after the training. It's not saving it. I don't know why. And then it's returning the predicted, and then the weights. That happened after readjusting. So we are going to run this, and it should work, hopefully. If not, I'll be very upset. Okay. Cool. Losses are converging. It'll probably stop. I doubt it'll be good the first time around because the weights are randomized in this example. And then for each child, for each generation, we're appending the weights that led to that, and we're scoring the prediction based on the sparse model. And this line 412 is exactly what I meant when I said we're looking at the score. I wonder if it's still here. I guess it's not. I gotta stop using Zoom Share. I gotta stop using Zoom Whiteboard. I gotta start using. I think I showed this last time. Found this really nice. It's called Clicky. It's just like MS Paint kind of thing. I think I'll use that from now on. Yeah, but what that line does is it finds the score. Score of y. This is going to be y. It's called ypred given our dictionary, and this dictionary basically represents the sparse model we're dealing with. That's a D. Yeah. Okay. Things will go for about 200 iterations. The loss function is MSE, so it should. Yeah, patience 3. It should stop sometime if it doesn't get better, but it might keep going. Anyway, not the worst thing in the world. But then after this finishes, after 408 finishes, we have the sparse model, which is from all of the data. And then we have the YPRED, which is just for the given generation of the generation. And then, so like the generation dictates what data we use, what samples we use. The children dictate the weights. Okay, they finished. So now we have YPRED, which is 5 by, this is of the 5 samples in this generation. We have 128 points, and then we have the weights associated with it. It's kind of funny. One of them actually, there's just a constant 1. It's funny. Oh. 3, okay. Okay, I don't know what's happening there. But if we go to, we're going to append it to child weights, and then we're going to look at the score function. The score function, that's what I've been trying to get to for the past 30 minutes. We're going to reconstruct based off the sparse model, right? And now we have the reconstruction. And they're not all zeros, actually. Some of them are non-zero. That's interesting. And then we're going to return the sparse activity of that. Of course, we skipped a line. And we need to somehow score this. It's 5 by 100 because we have 100 filters. So we need to score this somehow, and I'm not sure how. It looks like each row is a sample, and each column is a feature, is a dictionary element, because I didn't think I showed this, but in sparse representation, we have 100 filters. So that's the number of dictionary elements we have. Yeah. So what we need to do is figure out how best, we need to figure out how best to basically find an average score per sample. Sorry, score per sample and then average over each sample. So in the score function, what we can do, what I'm proposing we do, you simply do a, I'm gonna do mean, is it mean built in? Yeah, mean. For EN, we're dealing with the first one. Now we have just a tensor that's 100 long. Actually, I don't like this one. Let's do the first one. I think it's more interesting. It's 100. So I don't know what would be the best sort of way to score this other than, you know, take the mean. I don't know if that's interpretable because that doesn't tell us much about the contribution. That tells us whether across, so the mean in this example, that statistic tells us the average contribution of each of the dictionary elements. I don't know what you should expect to see. Maybe it's that the standard deviation needs to be high. right? Maybe it's that the standard deviation needs to be high, and the higher the standard deviation, the better, it's able to reconstruct it. What I mean by that is, if for this sample, if we're looking at just one sample here, I have to learn how to use this. If for this sample, we have a tensor of 100, the best case scenario is that we have, in some of the dictionary elements, we have ones, right? And in other dictionary elements, we have zeros. That's the best case example. Maybe like this is 0, this is 0, this is 0, this is 0. Any mixture of ones and zeros are the best. Standard deviation wouldn't work here because we wouldn't get a minimum or maximum score if this was the case. Do we have any suggestions? Actually, some of these are unbounded too. I would have figured I figured that this was unbounded. I figured that this was bounded between 0 and 1. You'll notice that this one right here is, you'll notice some of them are greater than 1 and some of them are less than 0. So maybe I'm not interpreting them correctly. Any thoughts for what these activities might mean on a per sample basis then?
I don't have any thoughts, but I had one question.
Yeah.
So when you write sparse activity index 1, does that mean you are getting the dictionary of a single person from the database?
Which line?
Sparse, it's like a list, sparse activity.
Yeah. So I'm looking at the sparse activity per sample.
Okay.
Yeah.
So I guess we can take the mean of every element in the dictionary.
Yeah.
And then we can kind of create an average line and then figure out what are the ones and zeros.
Yeah, I was saying we could do that, but like we have to think about like our objective or loss. We have to think about like our objective function. Our objective function is to maximize the outcome that we want, right? And the outcome we want is one such that Y preds that resemble or that best match the dictionary are ranked higher than that of ones that don't match the dictionary. And I don't know whether the mean does that, right?
Yeah.
I'm gonna actually ping a Samu and say, are you available? Actually, copy URL. And I'll see if he can come in. I like having him on speed dial. It's pretty useful. Yeah, so So yeah, I'll stop again. Any questions about where we've gotten so far, and the problem that we're having, or the reason why we're unsure? You can ask any sort of questions, actually. I'm trying to get better and better at explaining this. If this was bounded between 0 and 1, it'd be easy. What I would propose to do if it was bounded between that is I would... Actually, I don't know whether... So I was going to say if we want it to be only zeros and ones, if that's the best case, we just find the distance from 0 if they're less than 0.5 and the distance from 1 if they're greater than 0.5. That would give us an objective function. One that we'd minimize in that case. Now, I don't know if negative values are bad as contributions, like how to interpret that. Does that mean for this negative value, does that mean that there is a negative contribution of that filter?
Or
I'm
else
not
we
sure.
can take the square and then pick out the distance from the lowest one.
Yeah, it
So-
might be, but there's information. There's a reason why it's negative, right?
I guess the point may lie beneath the label. Yes.
I'm not sure. Oh, something's fine, not available. It's fine. So, okay, some action items. I have to figure this out. And meanwhile, we can continue working on the paper. Andy's on it right now. Thank you, Andy. You might just have it on the background. I know I have this paper like open like all the time, just so I remember to do it. We need to talk about time series forecasting background. Alicia, your expertise would be great here. In the methods, talking about the architecture, and we could just do a simple table like we talked about last week, like we've done in our previous papers, and a network architecture for the time series forecasting, and then a network architecture for the sparse model, because that's something that's taken from Keras, I'm pretty sure. Yeah, it's you have an activity in a dictionary layer, and you can use that in the sparse model here. Cool. The data set, if anybody wants to, I know Ansh, you practice downloading the data set and you're familiar with like loading it in. Maybe mention not like the specifics for like what libraries we used, but like the file types and just general information about the PhysioNet database and what specific data set we're using. And then if you so do that, be careful, because oftentimes those data sets have citations that they want you to put in the paper. So make sure to include those. I'll have to think and talk to Osamu about how we want to score this, because we want to make it so that we favor the outcome we want with either a high or a low value, right? That's either objective or loss function respectively. What we want to see is we want Y-pred reconstruct to be indicative of we want Y-pred reconstruction to be indicative of a good match between the prediction and the dictionary that we have learned from all of the data. That's what we want. And in using that, we can select for each generation, we can predict the alpha percentage of the best children that have the best weights from the highest scores. And then we can modify and carry on those weights until we find the best weights, which would result in the best Y-pred. That's the general idea. And that's something we'd outline in the experiment, because the genetic algorithm function that I've been walking through today and trying to teach you guys is the experiment you would run. If you guys haven't yet, for the people on the call, I know Ansh has because we've kind of gone back and forth with questions. Please go to the Sparse time series forecasting directory on Drexel AI, repository in Drexel AI, and clone it. An attempt to run through the code and run through the data. If you have any questions at all, let me know. If you aren't able to clone it, let me know. I'd like for people to contribute. Changes for today. 0803. Cool.
I have a question.
Yeah.
So are we going to have an abstract for the paper, or it doesn't need it?
Oh, we need an abstract. I often do the abstracts last.
Okay.
Yeah, because the abstract really is an overall story of, the abstract is like an overall story of the paper. So it should include like motivation, methods, introduction, motivation, methods, background, and conclusion as a general scheme. And then IEEE often has like index terms. So those are just like keywords you want to include. So we'd include sparse coding, time series forecasting, long short-term memory, genetic algorithms, stuff like that. Yeah. So action items for me, I alluded to some action items that people can take, and when you start contributing to the paper, you feel free to add your name. My name first, Kim's name's last, and then in the middle is alphabetical. So Savek should go to after Nian. We can fix that later. Cool. I'll stick around for questions. I don't have much else. This is something I need to think about because it's not exactly trivial. It's dependent on how to interpret the activity. And once I get that information from Osama, I'll make an implementation, and then I'll report to you guys in the Slack channel about what I decided on doing. And then this is the last piece of the puzzle. After that, all you really need to do is just use the score after you run through the children for a given generation. You find the weights that are the top alpha percentage. So we use alpha, which is 0.05 for 100 children. We get the 5 top weights per each generation. And then those are the weights that we set to weights. We use the top weights to create new weights. So we might take we might pick the best one out of it, or we might take like an aggregation of all of the 5, and that's what we set as weights, and then that's what's used in weights random. So like this is going to be weights right here. So that's how it feeds back in. Cool. That is it for me. If you have any questions, I'll stick around. If not, I'll see you next week.
I have an odd request. It's like something unrelated to this.
Okay, what's up?
So when you finish the recording, can you crop out the first 5 minutes of it? I didn't know you were recording, and so like I wasn't prepared.
Oh, it's fine. Did you care a lot about that?
Yeah, so can you just like crop out the first 5 minutes?
Okay. Okay. No problem. Anything else? If not, I'll see you guys next week. Bye-bye.
Okay, bye.
Yeah.
See ya.